Hi, this is Sina and we're going to talk about the UPGMA algorithm. So what is UPGMA? UPGMA is a hierarchical clustering algorithm and is the abbreviation of unweighted pair group method with arithmetic mean. So it uses pairs to group the clusters, to group the items, and uses arithmetic means to update values, and we're going to see what that means. In bioinformatics, where we deal with biological sequences, for instance DNA, the input would be DNA sequences, or more accurately the distance of DNA sequences, and the output would be a tree, namely phylogenetic tree. And this phylogenetic tree shows that the relationship between these DNA sequences, for instance organisms, and shows us how close or far these different organisms are. How is this algorithm performed? We have, for instance, n sequences, and we consider them that they are of the same length. For instance, we have aligning these sequences using the central algorithm. For instance, we have n sequences of the exact same length. So we can calculate the pairwise distances. Here we use edit distance, and we're going to see how it works. And if we are going to repeat this cycle until we include all the elements of these table of this n sequences. First, we're going to find two closest pairs, two pairs with the smallest distance. We're going to group them, and we're going to update the table, which is the actually pairwise distances. For instance, if we want to pair and group A and B, we change their name from A and B separately to AB, and we update the distances in the table. Since we have merged these columns or rows, we're going to see that distance of C or any element to this merged A and B is the distance to A plus distance to B over 2, which arithmetic mean is used. For instance, considering that we have A, B, C, D, E, F sequences, 6 DNA sequences, we use the edit distance of these sequences, assuming that they have the same length again. So edit distance is actually the number of non-matching characters, considering that these ACGTs are represented as a string. For instance, in A and B, we see that the edit distance is 5, since they are different in 5 positions, 5 ACGTs. So, for instance, assuming that these sequences that we had result in these distances, we can start the algorithm. So we do not need to fill this matrix entirely, because distance from A and B is similar to B to A, and again C to D is to D to C, and we only need the lower triangle of this matrix. So we start to build a tree. First, we're going to see that the closest pairs are A and B, and we're going to merge them. Merging them, we're going to pair these A and B to AB, and we know that the tree that we built, the legs of this tree, the length of this leg is half the distance of A and B, so that the distance to A between A and B is 2 times this leg length. Here the leg length would be 1 because the distance was 2. So we update the matrix by merging A and B to AB and updating the distances. Updating distances, we see that distance of any element to A and AB, which is a merged grouped node, actually grouped element, is the distance of T to A and plus distance of T to B over 2, which is like an arithmetic average, arithmetic mean of these distances. Now we want to find the next closest pairs. There are two candidates, A, B to C, and C and E to D, but we can choose either of them. It's not important. We can first choose A, B to C, or if we can choose E to D. We go with E to D. Here we pair E to D again, exact way we did for previous step, and the distance of this and the length of the legs here will be 2, because the distance of E and D are 4. Again, we update the table in the same way using this arithmetic mean, and we see that we have 2 different parts of the tree, because it's not a complete tree now, we're going to continue until we form a complete tree. Here we have the distance of C and AB, which we had in the previous step again. Also, we're going to choose C and AB this time. Going further, we add C to AB, which gives us ABC. We update the tree by adding C to AB. Again, we have still two sub trees which will be merged later, and we see that the length of this is again 2, because the distance between A, B and C was 4, but since A and B had always this distance, has already distance of 1, we only need 1 length before the new tree hits AB. So we arrange it in a way that distance of A to C is still 4, B to C is still 4, and this distances are still maintained. So again, we update the table, and now we see that the closest distance we have is DE to ABC, which is 6. We continue and we merge these. Similar to the previous steps, we merge these, and this time these two subtrees are merged, DE to ABC, and using the same procedure, same steps, we see that the distance to D to C is again 6, E to C is 6, and similarly all these distances are maintained. So after updating the algorithm, after updating the table for this cycle as well, we see that the only element left is F, which will be added to A, B, C, D, E. Adding F to A, B, C, D, E, there is no table anymore. We have already added all of them. And pairing these, we have the distance, we have the length of 4 for the legs of this tree, and we see that F to either of these elements is 8, as we had in the original table, and all the other distances are also maintained as well. As you see, this table has an assumption which we'll discuss in the next slide. So we saw an algorithm which is quite simple and fast. It doesn't need many operations, and it's easy to construct phylogenetic trees. But the limitation is it assumes that the same revolutionary speed on all lineages, meaning that all these elements of this tree have the same kind of mutation rate. That's why the length of these legs are considered equal for the two sides, but which is not realistic, and it would not construct a correct trees if that condition wasn't kind of our assumption. That's the limitation of UPGMA, but other than that, it's a fast algorithm that can be used to build phylogenetic trees in a fast manner.